Okay, I said draw the valence orbitals here of formaldehyde right there. Okay, let's see what you guys came up with. So how do we analyze this? Well, maybe, what if you just draw it in a different way? What if you turn it to its side? Do you see how that kind of resembles a little bit what we did last time, where we looked at ethene? When we look at the double bond from that perspective, maybe that will help you see what's going on. But the first thing that we need to make sure we understand is, what is the hybridization state of that carbon? That is sp2. So let's draw the sp2 hybridized orbitals for that. So we have that. All right, there's our sp2 carbon, and there's our p orbital, right? Okay, then what is the hybridization state of that oxygen then? It doesn't sound like we're too confident in that one. Well, what if see, I can draw the oxygen just like that, and there's no formal charges. It's neutral. So that tells you how many lone pairs there are. There's 2 lone pairs. So now that I've added that component, what is the hybridization state? sp2, because there's 3 electron groups around it. So that is sp2 as well. So what does the electron configuration look like then for an oxygen? If we start from the beginning, let's go 2s and 2p. How many valence electrons are in oxygen? 6. So 1, 2, 3, 4, 5, 6. That's what it looks like in the ground state. But I said we needed to hybridize those, right? And you said a sp2. So we would do it just like the carbons. There's our p, there's our sp2, and now we have to put in these 6 electrons. Like that. So now what we're going to do, shrink that down a little bit. So we are forming a bond between the carbon and the oxygen, right? We have a single bond there. What electrons are going to be used? Well, we have to use 1 on the carbon and 1 on the oxygen. Which one am I going to use? Do I use these, that one, or that one to form the sigma bond between the carbon and the oxygen? Can we use the p orbital? Does the p orbitals form sigmas? No. So that one's off. Can we form bonds in an orbital that already has 2 electrons in it? No. So the only one that you have is that guy right there. And so what we're going to use to form that sigma bond is a carbon that has a sp2 hybridized orbital. And our oxygen atom is also going to have our sp2 hybridized orbital. And each one of those comes with an electron. And that's going to form our covalent bond, or our sigma bond. Carbon has what? Has some hydrogens attached to it. And so we see that carbon has 2 other sp2 hybridized orbitals. So we'll draw them there. And they should all be the same size. I'm just really bad at art. Okay, and so those electrons are accounted for. And then we have hydrogens that come in with our 1s. And there's our orbital overlap right there. And so what type of bonds are these? Those are 1s to a carbon sp2. But oxygen, so we've accounted for that electron. And then we see that we have a p, so that has to be perpendicular, right? With some phase, and it comes with an electron. So we've accounted for everything on carbon. Now let's finish up the oxygen atom. What we have in oxygen, we have a p, so we can draw that perpendicular to the plane, and we can add in our electron. So that's going to account for the double bond character. There's our pi bond that you see between carbon and oxygen. Now, if I asked you what orbitals are the lone pairs in? It's abundantly clear, isn't it? Those are the lone pairs. So draw those sp2 hybridized orbitals just like you did on carbon. You would have one in that direction and one in that direction. And those three orbitals, this one, and that one, are all in the same plane. Because what's the hybridization state? sp2. That means they're flat. All in the same plane. And so those lone pairs are shown right there. All right? So that's the diagram there for formaldehyde and how it all works. Do you see how it's the same principles that I used with the previous three examples? It's just, it's an oxygen atom. We just do the same thing. It just has more electrons. And we have to think about it a little bit logically on which electrons to use to form which bonds. Okay? Any questions on that example? No questions?
I have a question.
Yeah.
So in the textbook, there were some examples that showed the lone pairs attached to hydrogen. Is that because the positive charge of the hydrogen is attracted to the lone pair?
You said the hydrogen has a lone pair.
No, sorry. The hydrogen is connected to another atom, and that atom has a lone pair.
So what the textbook was talking about was something like this, possibly something like this here. Let's say CH3O. That question is just a little advanced for where we're at in the class quite yet. Okay. And I just don't want to go down that rabbit hole because I'm afraid we'll lose too many people. But we will definitely get to what you talked about shortly, especially when we get into the acid-base chapters. So, where did that go? Okay. So what I want you guys to do is I'm going to give you 3 molecules. You guys can all work together. And I want you guys to answer a couple of questions, okay? So the questions are, what functional groups? What functional groups are present in these 3 examples? I want you to calculate how many carbons there are. And then how many hydrogens? Okay, so I'm going to draw some zigzag structures. Now, zigzag structures, look like this. I can call those zigzag. I could call them skeletal. I could call them line structures. That all means the same thing. So you're going to be given these skeletal structures here. And here's the first molecule. Let's see, 1, 2, 3, 4. Let's see, let's start it off like this. Okay, so you're answering those 3 questions for that molecule. And then I want you to do this one. And we'll put the third one right below all of that. Okay, give that a whirl. So I'll give you a few minutes. And then I'm going to ask you guys to tell me the answers. Okay? What functional groups? How many carbons and how many hydrogens are there?
was one. Yeah. Fluid. Then this is 1, 2. Wait, no, it's not 6 fluid. It's not because it's a triple bond and then a 6. So it's a rate of 9. Oh.